quiz. Pay attention to this problem. Okay, I want you to be able to work a problem like it. Okay, so this is problem number 25 from your book. We'll do this one here. I think this is pretty good. Two construction contracts are to be randomly assigned to one or more of three firms. Firms number 1, 2, and 3. So two construction contracts are to be randomly doled out to across three firms. Any firm may receive both contracts. So this is sort of like the balls in the bowls problem, but you got 3 bowls and 2 balls, right? You can put both balls in the first bowl, or both balls in the second bowl, or one ball in bowl 2 in bowl 1 and one ball in bowl 3, and so forth. So anyway, each contract will yield a profit of $90,000 for the firm. And so then, if that's true, then find the expected profit for firm number 1. If firms 1 and 2 are actually owned by the same person, what's the owner's expected total profit? All right. So again, that's problem number 25 from chapter 3. Look it up in your book. All right. So the first thing, note that we're interested. It asks us to find the expected profit for firm 1. Can I just denote it like that? Is that okay? So that F1 is the random variable that represents the profit for firm number 1. Okay. Similarly, maybe we might want to use F2 as the profit for firm 2. Okay. You might want that in the future when we talk about the owner of both firms. It's not really fair, is it, to own 2 of those? All right. So F1 is a random variable, but guess what? One thing I can realize is that I can actually express F1 as, isn't it going to be $90,000 times this random variable n, where n is, say, the number of contracts firm 1 gets. Maybe I should write n1 like that for firm 1. Number of contracts firm 1 receives. Okay, that's a very useful approach. Try to write random variables as expressions of other random variables. Okay. So then, can I write down the distribution of n? Sure. One way to write it is like this. N could be 0 or 1 or 2, right? Sorry, n1. The number of contracts that the first firm gets will be 0 with some probability. I think it's like, can you figure it out? It's the probability that firm 1 gets no contracts. Maybe you want to pause video. Maybe not. Maybe you worked this out. Hopefully you got what I got. Okay. I'm not going to slug through that, but that's true. Okay, that's the deal there. Okay. Then how can I write the expected value of F1? Well, F1 is just that function there. It's just 90,000 doll hairs. Put the unit on there. Don't want to leave the units off, right? Now, we have a theorem that says that I can pull a constant out of that because, hey, remember, this expectation is just a summation sign, basically. It's sort of a special kind of sum. Pull that constant out of there at 90,000 doll hairs times the expected value of n. Okay, and expected value of n is pretty easy to get to. It's 0 times 4/9 plus 1 times 4/9 plus 2 times 4/9. And what's that spell? Gosh, can I get my calculator over here? Got 0 times 4/9 plus 1 times 4/9 plus 2 times, shoot, it's supposed to be a ninth, isn't it? 1/9. 2 times a ninth. 0.66666. It's like never-ending evil. Or 2/3. What's 2/3 of $90,000? 60,000 doll hairs. Very good. Hey, guess what? This kind of makes some sense if you think about it. You've got 3 firms, and they're going to sort of somehow kind of split a total of $180,000, right? 2 contracts worth $90,000 apiece. It's $180,000 for the 1, 2, 3 firms. A third of $180,000, 60,000 doll hairs. Okay. Now it asks us to find the expected value of the owner's winnings if this fat cat owns both firms. I could express it like that, right? Well, hey, guess what? Don't we have that theorem that says that I can write this as the expected value of F1 plus the expected value of F2? That's right. Sure can. What's the expected value of F1? 60,000 doll hairs. What's the expected value of F2? I don't know, but guess what? I do know that F1 is equal in distribution to F2, right? It's okay to write that. These are 3 random variables. They're not equal to each other because F1 might be $60,000 while F2 is 0. Okay, but we say that they're equal in distribution if they behave the same way. That is, if they have the same distribution. Okay, if I wrote out a distribution table for F1 and it looked the same as the distribution table for F2, which looked the same as the distribution for F3, I could write it like this, right? This equals this in distribution. So we put a little d up there to denote that. All right, so if this has the same distribution as F1, then I know it must have the same expected value, and so this is 120,000 doll hairs and 0 cents. All right, very good. Hey, let's do something else. Can we find the variance of F1? What's the variance of F1? I'm going to use that theorem that we proved about variance, that so-called inside-outside formula. Super useful. Couple things that all good math majors need to have are, number 1, a calculator, and number 2, you got to know this formula, the inside-outside formula. Right? Looks like that. All right. I don't know how to do this. I know what the expected value of F1 is. It's $60,000. I just got to square that there, subtract it from this other stuff. Let me come down here and work out this other stuff. Okay, I'm just going to take this, come down here with it. Expected value of F1 quantity squared. Well, what is F1? Let's see. F1 could be 0, right? So this is going to be 0 squared times the probability that F1 is 0. So what's the chance that F1 is 0? It's 4/9, right? I got that from looking over here at the distribution of N1, because F1 is 0 if and only if N1 is 0. Isn't that true? If you get no contracts, then you get no money. If you get no money, it means you got no contracts. Plus, let's see, F1 could also be what? F1 could be 90,000 doll hairs, right? I need to square that because I'm finding the expected value of that thing squared. And what's the chance that F1 is $90,000? It's 4/9, right? Plus, finally, they could get both contracts. Greedy so-and-sos. Square that times 1/9. Okay. See that? So what do I have there? I've got 0 plus 90,000 squared times 4 divided by 9 plus 18 minus 2,467 minus 5, carry the 1, something or other, delete, back up, divided by. Hope this is right. I got that. 90,000 squared times 4 nines plus 1, 8, something, 180,000 squared over 9. That's a huge number, isn't it? Geez, 1, 2, 3, 4, 5, 6. I don't even know what is that? Is that like 7.2 billion? Yeah, I think so. 7.2 billion. Could that be right? Yeah, it is. Okay. Yeah, that's right. These variances get real big, and that's why a lot of times we talk in terms of standard deviation, because if you take the square root of this number, it'll be small. But anyway, so this isn't quite the variance. This is something that we call the second moment, and we'll get to that in a little bit. But I'm going to take this now and stick it back into, up here. Don't forget to do that. This isn't the final answer. 7.2 times 10 to the 9th dollars minus, I got to take, the expected amount of earnings is $60,000 and square it. Oh, by the way, yeah, I guess this guy has units of square dollars, doesn't it? Don't they? Yeah. Okay, so got take all that minus 60,000 squared. I get, looks like 3.6 billion. 3.6 times 10 to the 9th squared dollars. What the heck is a square dollar? I don't know. What's the standard deviation? It's the square root of that. So I get 60,000. No. Yeah. No. Yeah. $60,000 is the standard deviation. That is a happy accident. Okay, that's just a big fat coincidence that the standard deviation happens to equal the what it does there, the expected value. Okay. All right. So be able to work a problem similar to this on the quiz. Have a nice weekend.